Okay, so you would have seen got your exams, and even before that, you would have seen your grades. And general comment, on an average, the class did well. The median score was 86.5, which is decent for them. It's what's expected typically. Median doesn't mean too much for a small class like this. But the point is that most people did well. And if you were in the borderline, if you didn't do as well, there's still time to catch up because there are 3 exams and the homeworks cumulatively count as much as an exam. So there is a lot of other stuff to go. There's a lot more to be done in the semester, so you have a lot of time to catch up to improve your grades. So if you aren't one of the lucky ones who did really well, there's no reason to lose hope. There's a lot of time to recover. But be sure to talk to me. What you should do is take a look at the exam and compare it with the key that I posted. The way it works is that, as I told you, for the exams, the graders went through that and I've gone through it. So that's why you will see comments in 2 different colors. I'm careful to use a different color pen. I don't remember what I used red in one and I didn't do black in the other, but it's different from what the grader used. So you can easily see what changes I made. Usually you will find that I'll add some points depending on, as I said, the point is that the graders go by the key, and if you made a mistake, you lose points. Whereas when I go through it, I try to make sense of what you did and what you intended to say, and maybe it made sense. Maybe it was really a small error that looked more serious than it really was, and so forth. But the point is that at times there are significant changes. At times it's half a point or 1 point, but at other times there could be significant changes after I've gone through that. So, point of all that is that the exam, I have gone through the exam, but that doesn't mean that something has not been missed. So you should definitely look at it, and you're more than welcome to come and talk to me. If there are any questions about the grading, don't hesitate to talk to me. And not just about the grading. I mean, if you see the key and you still don't understand why something was answered in a particular way, if you need to learn more about the topic, you're really encouraged to come and talk to me to clarify the point. As always, I've told you that when we go ahead, a lot of the material we did so far will continue to be relevant for the rest of the semester and beyond for next semester too. So if you look at constant acceleration formulas, we're still using them. We'll continue to use Newton's laws. We're going to continue using them. So understanding the material, especially in the first exam, is really important because it forms the core of what you're going to do later on. As you go ahead, you will see for the second exam, there are topics that will be important for that exam, but you like rotation. But you really won't get back to it beyond that. So there will always be topics that will be specific to that particular exam. But what you did in exam 1 is fundamental. It's what you're going to use in everything you do beyond this point. So it's useful, it's important. Even if you miss something in the exam, to make sure that you go back and figure out what went wrong and talk to me if you can't figure out, still can't figure out what was it. Okay, those are general comments about exams, about the exam. Now, the homework. Okay, so let's, as usual, make a few comments. Maybe I should take a look at, I talked about 4 last time, but since it's still out, maybe I should take a look at that too. I was planning to look at 5, but let me take a look at 4 too. This is 5. Because last time when I talked to you, I hadn't posted the hints, which I have now. So you should definitely look at the hints. For some of those questions, it's important. So I won't repeat what I said earlier. We talked about it last time, like question 1 is straightforward. I won't say anything about it. 2, I'm not going to say much about it. 3 is what, do look at the hints, because 3 is a case where you do three different, oh, wait a minute, let's see. Should be. Well, let's try starting it again. It's supposed to be on, I guess. It was off for so long it turned off, so we'll wait till it comes on. So yeah, I won't wait till it warms up, till the projector warms up, I'll just talk about it. So the problem I'm talking about is number 3 in set 4, which has to do with the sled being pulled at an angle. So the tension is applied at an angle. The point there is, the first part is straightforward. It's just the work energy theorem. It asks you what's the total work done on the sled. And you have enough information about the kinetic energy to calculate that work. For B, C, and D are actually all together. It looks like the questions, the order is, what's the work done by friction? What's the work done by the tension? Seems very straightforward, the way you usually calculate the work done by various forces, and you plug it into some formula to work out something else. But in this case, that's not the way it works. It turns out, and it's because the unknown tension plays a role in the horizontal direction as well as the vertical direction. The friction depends on the normal force, and the normal force depends on the vertical component of the tension, which you don't know. So it turns out that both B and C cannot be answered numerically at this stage. So you have to write down expressions for work done by friction and work done by tension. They will involve that unknown tension T. And after you solve for that, in D, you determine the tension, then you go back and plug in the value of tension into those formulas that you wrote down in B and C. So in a sense, you're doing B, C, and D all together. So careful about that. Check.
Isaac.
Let me try turning it off. Hopefully that takes care of it. It doesn't work this time, we just managed without projectors for today.
There must have been a ghost or something, because the door opened and then now this
Boy,
is
that was weird, right? Yeah. That was weird.
Do you mind if it doesn't work, do you mind if I just record your voice? Just because it really helps.
Oh, no, the whole thing is being recorded. That's not it. The problem is not the recording. The problem is just with that screen
okay.
there.
Okay.
Oh, it's being recorded on Zoom, right?
Okay,
here.
perfect.
So, and the slides will be there on Zoom. So when you watch it if you watch the video, you're going to be seeing those slides.
Okay, perfect.
But what Usually what we do is while we are in class, we project there, and
Yeah.
we look at it over there. That part is not working. For some reason, it's not projecting.
Physics go.
The lights work fine.
Can you call the tech department? Is there? Maybe not at this time. Yeah.
Yeah, fine, okay. But this is just for our convenience. So what you see in the video is not this. What you see in the video is the shared screen. Okay, just being there. Okay, so this is the problem I was talking about. So as I said, B, C, and D will all be done together. You write down expressions in B and C and solve them. You solve that expression in D because you will use the information you got in A to solve D, and that will give you the tension. You will then go back and plug in that value of tension into the expressions you derived in B and C to get the actual numbers for the work done. Okay. So among all the problems, that's the one that takes a bit of work. 4 is actually a very simple problem, but a number of people ask me this, so the wording is a bit confusing. C and D are completely trivial. So it is just the whole point of C and D is to show you that, well, there are other units that we use in life other than joules, and to have an idea of how these things compare. So A and B are what we have been talking about so far, power and work done and so forth. In C, all you're going to do is saying that, well, whatever energy I calculated earlier, the energy needed for the jump, the energy that was used for the kinetic energy is equal to the kinetic energy when it left the ground, the person left the ground. That energy is really 1/4 of the energy developed by the muscles. So the energy created, expended by the muscles is 4 times the energy that you determined earlier. That's all it says. So multiply by 4 is all you're going to do with that part. And in D, it's even simpler. All you're going to do is to divide by that conversion factor to get the answer in kilocalories, or what are called food calories. So C and D are really trivial. Okay, we've talked about 6 in some detail. So again, 6 is an example of how you need to use ideas from earlier sections. So you're going to be using Newton's laws there to determine what the force is. And then you're going to be calculating the work done by that force. The tension, you're going to use Newton's laws to calculate the tension, which will then give you the force. Okay, so that's that. Now we go on to the set that's due on Sunday. So don't forget that. So don't forget that because of all that delay in set 4, all the extensions, there are actually 2 sets very close together this time. Plan on that. One's due on Wednesday and one's due on Sunday as usual. So Sunday one is not earlier than normal. It's at the normal time, just that the Wednesday one has been delayed so enormously. So Wednesday and Sundays are the due dates. Keep track of that. Problem 1, I've given you hints. And maybe after we finish it, maybe I'll come back and discuss it. I'll give you more examples, and more of a reasoning, more of a motivation in case you need it. But I've basically given you something that you need to know when you do this problem, because I'm interested in the work energy, the conservation of energy calculation. But this problem is a little more subtle. You need to remember, and we've talked about this when we did pulley systems, and we did movable pulleys, not directly this, but sort of we hinted at this when we talked about it. We talked about how the force gets multiplied when the force acting on the movable pulley is actually double the force applied by M2, double that of M2. But then that force produces a displacement that is half of what M2 is going through. Because if you pull M2 by a certain distance, d, that gets split in two when that rope goes around M1. It has a left half and a right half. So when you pull it up, M1 is going only half as high as M2 is going down. So that's important when you calculate the work done or the change in the gravitational potential energy. Keep track of that. So the distances traveled by M1 and M2 are not the same. And in the same way, if they start from rest and in a given time, they're going to be moving half the distance, one is going to be moving double the distance of the other. Obviously, it's moving twice as fast. So the speeds are not the same either. So M1 and M2, the distances moved are not the same, the speeds are not the same. Be careful of this when you write down equations for a kinetic and a gravitational potential energy. Nothing much to say. The hints, I posted the hints this time, if there's anything to be said, but conservation of energy. And always, in all of these problems, remember, there is this one equation we're going to be using. Kinetic energy at 1, K1, plus gravitational potential energy at 1, plus elastic potential energy at 1. If there are no non-conservative forces in the problem, you stop there and you say, well, it's equal to the same things at 2. So that's conservation of mechanical energy. K1 plus UG1 plus UL1 equals K2 plus UG2 plus UL2. That's conservation of mechanical energy. But supposing you have other forces other than gravity and other than springs. Remember, as far as we are concerned, those are the only two conservative forces we'll consider. So if your problem has any other force, friction, for instance, there's going to be a W other. There's going to be a work done by non-conservative forces. And work done by a non-conservative force just stays as it is. It's not converted to change in potential energy. You can't do that. So the way you think about it now in the presence of non-conservative forces is you say, I started off with a certain amount of mechanical energy. That was K1 plus UG1 plus U elastic 1. But because there was a W other, because there were non-conservative forces doing work, that changed. So K1 plus UG1 plus UL1 plus W other produced a new mechanical energy.
When you say U elastic, that's like a spring?
Yeah, exactly. So whenever spring and elastic mean the same thing, I'm always considering springs that obey Hooke's law, ideal springs. So it's always 1/2 kx squared.
But we're going to be using elastic as meaning. So I guess when there's collision, does elastic mean the same thing?
Oh, no, good point. That's a different usage of the word.
Okay.
Thanks for pointing it out. It is a different. So here, elastic is in the sense of a spring that you can stretch, the usual sense in which we use the word elastic. So something is elastic, you can stretch it and let it go. It goes back to its original configuration. That's how a spring behaves. That's the sense in which when we are using this idea of elastic energy or elastic force, kx and 1/2 kx squared. But what we are going to talk about when we do collisions, when we talk about elastic collisions, well, they're not totally unrelated. There is a relationship there. But the way we will use it, it'll be very specific. Elastic collisions will mean that that collision conserves total kinetic energy. But it's because of the elastic properties of the colliding objects that holds true. So there is no deformation. Things are returned to their original configuration. So they are related. But don't get confused between the two. Okay, coming back to the energy discussion, when I say elastic energy, I mean spring energy. So in a problem, you might have springs, you might have gravity. You don't have to have all these terms in every problem. So the three possible things are you could have spring forces, you could have gravity, you could have other forces. Spring forces are always dealt with using 1/2 kx squared, the spring energy. Gravity is always dealt with using the gravitational potential energy, mgh. Everything else is dealt with using work done by that force. That's it. And that's the exact same equation you're going to be using in any of these problems. So in problem 2, there are no springs. There are no known conservative forces. So all you have is kinetic energy and gravitational potential energy. Well, interestingly, there is a force, there is tension. There's tension in the string. But you see, this discussion doesn't point into, we've never asked anything about tension. We don't ask about work done by tension. We don't discuss that at all. That's because if you look at the picture, you will see that the tension is radial, the displacement is tangential along the arc. They're perpendicular to each other. The tension is perpendicular to the displacement, and we know then it doesn't do any work. That's the reason that that force doesn't play a role in our energy analysis. Tension does not play a role. It's only gravity that matters. Here we have elastic energy. This is problem number 3 with the bungee cord. Is something that involves kinetic energy, gravitational potential energy, and spring energy, because the bungee is taken to be a spring. But you don't have non-conservative forces. There is no friction here. You're ignoring air resistance. So that's the problem. So if you look at all these problems, you will see which of these quantities plays a role in that particular problem. Problem 2 has just kinetic energy and gravitational potential energy. Problem 3 has kinetic energy, gravitational potential energy, and spring energy. When you do the calculation, be careful. The spring energy, the elastic energy, depends on the change from that unstretched 30. So when you use the formula, when you use 1/2 kx squared, remember that x is not whatever the length of the cord is at that time. It's the change from 30. So keep track of the 30 when you do. Okay. One more thing to note, and often people end up doing this, because you say in A, so because the person is at rest at some point, 65 meters, it said the person is at instantaneously at rest, it's the lowest point, so the person is at rest and turns back. So a natural tendency to use is kx equals mg. The person is at rest and you think kx equals mg, but that's not valid, because remember, kx equals mg is applied when you have equilibrium, when you have forces balancing. At rest for an instant doesn't mean equilibrium. That person goes down, stops, and gets pulled back. So there is no equilibrium at that point when the jumper is at 65 meters above the river. He's instantaneously at rest just for that instant. His velocity is 0, but the force acting on it, the net force, and the acceleration is not 0. So you cannot use kx equals mg. You have to use an energy analysis. You can say the kinetic energy is 0, sure, because the person is at rest, but the net force is not 0. So always distinguish between equilibrium and instantaneous rest. They're different things. Again, this involves gravitational potential energy and friction. Friction in just one segment, AB, otherwise usual gravitational potential energy and kinetic energy. Another problem involving, so springs, it's a straightforward problem. I really won't talk much about it. So springs, friction, and gravitational potential energy. This is a problem that will make more sense after we finish with this. We're going to start working. We're going to continue doing problems from that unit. We haven't finished with those. We have 2 problems left. The first problem we do will actually be very closely related to this. The point to note is, as I mentioned, either here or in the hints, it's convenient to take the gravitational potential energy of the system to be 0 at this level, at the natural length, at the top of the spring when it's uncompressed. It's not essential. You can take it somewhere else. It's as I told you, where you take the gravitational potential energy to be zero is actually arbitrary. Physics doesn't depend on that, but it's just convenient to do it this way. So if we do that, what you see is that in the initial configuration, the initial situation where the elevator is at height d above that point, it has a gravitational potential energy mgd. But when it comes down, after it makes contact with the spring, it keeps pushing it down. What we have asked about part A has to do with just when it makes contact. That's fine. There's no, up to that point, the spring is not involved in the problem at all. Because remember, the spring plays a role only when it's stretched or compressed. If it's at its natural length, it doesn't have any elastic energy, any spring energy. And since we always consider ideal springs, it doesn't have any other kind of energy. It could, even if it's oscillating, we don't really care. As long as it's compressed, if it's not compressed or it's not elongated, we don't really care about what the spring does. So up to that point, up to part A, the spring doesn't matter. But for B, it does matter because now the elevator is compressing the spring. So when the spring is being compressed, you have to keep track of two kinds of energies. One is obviously the spring energy. It's getting compressed. So sure, there's the 1/2 kx squared energy. You won't miss that. You won't forget that. But as it's being compressed, the elevator is going below what you took to be the zero level. It's going below that level. So now it's picking up a negative potential energy. It's a small number. It's not going to make a great deal. It's not going to make a great difference in your numerical result. But conceptually, it's important. And if you don't write down that term, you will lose credit for missing the concept. So when the elevator goes below that zero level, you should account for the change in the potential, the change in the gravitational potential energy, as well as the spring energy. And as I said, we're going to do a problem where we'll do precisely that. Next. Yeah, we are recording. Today is a bizarre day. Yeah, fine. Okay. Let me make this full screen. Right, so let's start talking about problems. So, this is the one we can look at. Much of it, all the calculations are here, so I probably won't write. So if I need to, I'll go and write stuff on the board. But having said that, no, maybe the first one I actually will write stuff on the board. Let me write the first one, then I'll come back to this and start working out this problem because it's useful to write this part out. The first part, schematically, what we're going to do is there is this trampoline at some level. Person is at some height h. Person jumps from a height h. And compresses. So it's really like there are multiple springs, but we don't really care. A trampoline, there are multiple springs, but they're all together acting as a system of springs. So what this person does is when they jump, person starts off with a potential energy U gravity equal mgh. Again, we are taking the top of the trampoline, the unstretched spring, to be the zero of the potential energy, exactly what we did do in the elevator homework problem. So we take UG to be zero at this. That's our choice. So to begin with, that person has gravitational potential energy, MGH. The spring plays no role because it's not compressed or stretched. So U elastic equals 0. And that person is at rest to begin with, so kinetic energy equals 0. So all of this, but if you want, you can call it 1, 1. I'm not sure what notation I used. Problem. We'll get to it. At this stage, when the person just reaches the trampoline, it's still not compressed. So UG is 0 already at this level. U elastic is still 0. But K, whatever it is. Well, and you know what it is. It's just MGH. What else is there? If you're going to equate the sum of those to the sum of these, we're going to apply conservation of energy because there are no non-conservative forces. All you have is gravity. So we'll use this to calculate the kinetic energy at this level. And from there we'll calculate the speed. That's the first question they ask. What's the speed? Well, actually, this is what they ask in the homework problem. I'm not sure, I don't remember what exactly they asked here. We'll look at it in a minute. So we'll do it. But after that, what happens is the trampoline gets compressed. So it goes down by some level D. This is where you need to be careful. So this is they're talking about the maximum compression. The maximum compression, the person is at rest. Again, that's what maximum compression means. Instantaneously at rest. It's going to be pushed back, but instantaneously this person is at rest. So K, call that 3. I mean, don't take this notation too seriously. It may not match the labels. Physical quantities are fine, but the 3s and the 1s and the 2s may not be what I used when I wrote out the key. So at this point, the kinetic energy is 0. But the other 2 is what we have to be careful about. U elastic is equal to 1/2 K D squared. As the compression is by D compared to the natural length that has been compressed by D. So it's 1/2 K D squared. But what you shouldn't forget is that there is a gravitational potential energy. Now, what do we write for this? This is very Be careful. What's the expression that we write down for this? I'm going to use minus mgd. By doing that, I'm making a choice. By writing it as minus mgd, I'm explicitly saying that I'm going to take d to be a positive quantity. If I were to write just mgd, d would be negative. But by writing it as negative mgd, I'm saying that, yeah, I'm taking d to be a positive quantity. So what does that mean? So this d that I'm talking about is the magnitude of the compression. Remember, usually when it's compressed, we say x is negative.
What's the significance of choosing it to be magnitude?
Simply to match my formula there. You could say that I'm taking D to be negative and I'll take the gravitational potential energy to be mgd. That's fine. The reason is, as you will see, all of this, when you apply conservation of energy, you're going to end up with a quadratic equation. You have a D squared term, you have a D term. You're going to end up with a quadratic equation for D. When you solve that, you're going to get a positive and a negative root. Which root do you pick? That's where it comes. So if you make this choice for your gravitational potential energy, we make this choice because for most people, this is more natural. To say, yeah, it goes below, D is the distance, it goes below the 0 level, so the potential energy is negative mgd. And D is whatever the positive quantity. So if you do it, it doesn't matter for the elastic, because that's a d squared when you care if it's negative or positive. It does matter here. So if you choose your gravitational potential energy to be at the form minus mgd, you are saying that I'm choosing d to be a positive quantity. So when you solve that quadratic equation, you pick the positive root. That's it. But as I said, there's nothing to it. You could very well say that at this point, I'm going to write it as just mgd, do the problem, and pick the negative root. Perfectly. Okay, so this is what it is, and let's look at the detailed calculation. I don't need to write all that down because it's just all of this with the numbers. So this is an 80 kilogram. And that's the mass M. Jumps from a height 2.5 meters. That's your H in what we talked about. Onto a platform mounted on springs. So as the springs compress, he pushes the platform down a maximum distance. So as I said, I hadn't read the problem. I was talking about the homework problem. In this case, turns out that they've actually given you the D. So it's the same calculation, but they've told you what T is. In fact, they told you D and they're going to ask you to calculate K. It's the same equation, but they're going to ask you to solve it for K, little k. So it compresses it at maximum distance 0.24 meters below its initial position, and then it rebounds. The platforms and the springs have a negligible mass. What's the man's speed at the instant he depresses the platform? 0.12 meters. Okay, so then we'll talk about the next one. So it turns out here that for answering part A, you need to know K to do this kind of calculation. We'll look at that. But they haven't told you explicitly to calculate K, but that's something you need to do. So the first thing is we're going to do an analysis just like we did here, same equation, we're going to use that. But we're going to use that to calculate the spring constant K. And then we're going to do the same kind of calculation, not for the lowest level, but for something intermediate. So at some intermediate steps, that person is going to have a kinetic energy, a gravitational potential energy, and the system is also going to have a spring energy. They're going to be all three terms. But exactly the same equation, same procedure. We're going to use that to calculate what they ask for, the kinetic energy, and from that, the speed. And then we'll come to what the next part B has to do. Conservation. The first part, as I told you, it's very simple. The spring doesn't play a role at all. Again, I'm talking about the homework problem. Here it is. Sorry. This is going back to this problem. There you go. K1 plus UG1 plus UL1 equals K2 plus UG2 plus UL2. These are the quantities we wrote down. At the top, the zero kinetic energy, potential energy, gravitational energy is MGH. Spring is uncompressed, so zero. In the final stage, when it's fully compressed, the system is again momentarily at rest, so K2 is zero. Elastic energy is 1/2 kd squared. And the gravitational potential energy, as we just discussed, is negative mgd. Now we solve for K. So the first step is to use the information given to solve for the spring constant K. But that's not what they asked us for. They asked us for the speed when that person is at a hasn't fully reached the maximal compression, when it's in some intermediate stage. When the spring is compressed only at distance 0.12, that is half of the full distance, 0.12, we have the same equation. The left-hand side is exactly the same. We're still comparing it to the top. 0, MGH, 0. On the right-hand side, we have a kinetic energy, because the person is still moving. 1/2 mv2 squared. And otherwise, it's very similar to what we had before. We have the gravitational potential energy minus mgd2. We have the elastic energy, 1/2 kd2 squared. What are we solving for now? Solving for V2. So it turns out that in this way of formulating the problem, there is no quadratic equation to be solved. We've been given that information. Whereas when you do your homework problem, it's the other way around. The unknown is that distance d, so you have to solve a quadratic equation. That is the same equation. So we solve for it. We find out what we use.
We need to be concerned with the direction of motion in this case, so whether velocity was positive or negative.
No, because we only talked of energies, and the kinetic energy is 1/2 mv squared.
But for our answer,
Oh, okay. That will depend on the way we are talking about is when the person was on the way down halfway, but it could be reversed. The person could become, because there is no friction involved here, this conservation of energy could be going the other way, could be going all the way down and coming back. So it would be symmetric in this particular case, but not in the case where not in our homework problem, because in the homework problem we had friction.
since this is going down, I guess it depends on how we're choosing our axes, but with everything else defined as it is, would our answer be negative? With the velocity being downward?
Sure, but what they've asked for is the speed.
Oh, okay, I'm sorry.
But if it's the velocity, you're right. Okay, what's the other question? There was about stepping gently onto it. What do we mean by that? Is that we don't give it an initial kinetic energy. That's one thing, obviously, nobody's jumping onto that. More importantly, that talks about equilibrium. What we're saying is that, but the gently part has to do with equilibrium. So forces are balanced, the whole thing, there is no acceleration involved. At any given time, there is a state of equilibrium. And that's what we're going to be using. So that's the difference between something that's oscillating up and down, that's not in equilibrium, and case B, where you have deliberately created an equilibrium situation by doing everything in a gentle way, by just stepping on, making sure that forces are always balanced. And in equilibrium, it's actually very simple. That's when you can use that you can equate forces. Once you know there is an equilibrium situation, you can equate the net force is 0. And the only two forces are gravity, the weight, that's mg, and the spring force kx. And they have to be equal and opposite. That's what. So equilibrium situations are always easier. But you don't have to guess. I mean, the way things are stated, you'll be told. When you're asked a question, you'll be explicitly told something is in equilibrium or it continues to be at rest. And in some way, it'll be unambiguous. But the point to note is the other part that's more important. You'll often have situations where something, especially when you have springs involved, at the turning point, the system will be momentarily at rest. You cannot use equilibrium. Okay, the next problem. So this is something that, we actually had forgotten to do it again. Last time we brought the equipment out, the demonstration out, but didn't have time to show it. But today we didn't bring it out. But anyway, you have seen similar things before, so you can imagine what happens. Oh, incidentally, I forgot. Actually, the way I had set it up, based on this, I went ahead and gave you the answer about gravitational and elastic energies. But it was supposed to be a preliminary question where we think about it and then come to the answer. We're going to do the same thing with this one. Okay, so we'll skip that first question and get to the second. In this, what is happening is that there is this ride and there is a car in an amusement park. Rolls without friction. Where do they say that? That's because we want to, it's basically rolls without friction, it just slides. So we are actually ignoring rotational motion. We're going to come back to this. And rotational motion is important. It will make a difference. It'll change the results that we're going to derive today. So what we're going to do today is an approximation when we ignore rotational motion. Let's just keep that in mind for later. So if you ignore rotation, so then it basically slides down and goes around. Starts at some height, comes down the track and goes around the circle. So what they want to know is what's the minimum height h such that it can make it all the way around the loop. So that's the first question. Before doing any calculations, we're going to sort of think about it conceptually. Okay, so this was the one that, let me just show you. This is the, no, this we did. So, yeah, this is the one that I was planning to ask you about. Well, we already discussed it. And problem two, the one we just did. What happens to the gravitational and elastic potential energies? We are done with that. So the next one has to do with this problem. Well, it's the same, the question we're discussing now. Before we do any calculations, we try to get an idea of what we expect. So we try to guess at what that minimum height they're talking about should be from whatever we know about conservation of energy so far. So remember, friction is out. We don't have any, we've been told that friction doesn't play a role. So it's your normal conservation of mechanical energy. You have gravitational potential energy, you have kinetic energy. So the question is, well, R is the radius of that circular track. So the first thing you try to guess is, well, what's the minimum value of h for the car to make it to the top? Is it R or 1.5 times R or 2R or greater than 2R? Just what you expect based on whatever you know about conservation of energy. Okay. So Nathan, is it working today? Still not?
Not yet.
Okay, let's work on it later. Yeah, that's fine. As I had kept that, as I told you, I had kept that test question on, but I didn't see you responding, so I assumed that there was some problem. Now, we'll fix it. Maybe I'll just subscribe you again.
Thanks.
I'll just go ahead and do that, but yeah, no mind to it, we'll look at it.
The risk of public humiliation, I'm gonna say it's R. It's my poll response.
Well, we'll talk, yeah, but that's what we're going to work out. Obviously, it's a non-trivial answer because we're going to spend time working stuff out. Okay, that's 0. Let's see what people talk.
Oh, wait, I'm done.
Doesn't matter, it doesn't matter at all. Okay, well, let's see what the right answer was. It's actually 1. It's actually more than 2 are, 1 person guessed. You could have thought to guess because the whole point is you're doing a whole problem on it, so it's going to be something non-trivial. And we'll see why it's not trivial. We can sort of guess why. Actually, we can talk about why it's not trivial. That's why it's interesting. We'll do the calculation, we'll get the right number, but we'll see why it has to be more than 2. Well, 2R is a reasonable guess because you would think that, well, the height at B, the maximum point, is 2R. Gravitational potential energy there should be mg times 2r. So if you start at the same height, gravitational potential energy goes to kinetic energy, comes back to gravitational potential. Looks like you're doing fine. You have enough energy. So the problem is, remember, you want to stay on the track. There's something going on there. And we've talked about this when we did forces. We said that the car can stay on the track only if there is a normal force. So there has to be a contact. And if there is a contact, there is a normal force. So that's our condition for the car to stay on the track, a non-zero normal force. And in the limit, the zero normal force is where it falls on. So we want it, that's the limit we are looking for. But if our gravitational potential energy is exactly what we had at B, what that means is when we get to B, our kinetic energy is 0, the speed is 0. But remember that N, that normal force, depends on the centripetal force, centripetal acceleration. It depends on the V squared over R term. You're going to write all that down. But that's what it depends on. But even simply, why do you have a normal force? Why is it pushing in? Because the car is trying to fly off. Because due to inertia, the car is trying to move in a straight line. It's trying to fly off the track, away from the track, and the track has to push it back to keep it inside. That's where you get the normal force. So at every point, the car is trying to leave the track. It's going to continue in a tangential path, but the track has to push it in. It has to provide the centripetal force to keep it moving in a circle. But if the car is not moving at all, if it's at B, if the car is at rest, you don't need a centripetal force. It just falls. All you have is gravity and it falls. That's the problem. So having just MGH is not enough because you won't have, there will be nothing. It won't be in contact with the track by the time it gets to the top. So that's the condition. What we need to say is that at the top, we need to have that normal force, which is 0 in the limit. And we start with that, and that n equals 0, as we have seen before, we've talked about this before when we did the Newton's law unit, that n equals 0 is going to give you a V minimum by applying Newton's law. And that V minimum is going to correspond to a minimum kinetic energy at the top at B. So the energy that you really need at A is the mg times 2r, which is the potential energy at B, plus the minimum kinetic energy at B that you need to have a normal force. All that is what you need at A. So the H will turn out to be higher than 2r. Okay, let's work on that. So the first and the next one is trivial. The next one is just saying that, well, it'll turn out that you will need, the answer turns out to be 2.5, 2.5 times R. But then they say, well, supposing you start off with an even higher height. Suppose you start off at 3.5 times R. So obviously you have enough of a height for it to go around. But the question they ask you is not that at B, but they ask you for to do the calculation at a different point at C, at this point C. So it's the same conservation of energy calculation, but not at B, but at C. That's what they're going to do in part B. Okay, so as you said, the first thing we do is force calculation, Newton's law calculation at the top, where we try to figure out what the minimum speed is. And we write down, we've done this before. The track is pushing down, so n points down, so negative n. Weight always points down, so negative mg, equals the centripetal force, mass times the centripetal acceleration, which is inward, because the centripetal acceleration is toward the center, it's down at the top, so it's negative mv squared over. And for the minimum, we have n equals 0, which means mg equals v squared over r, and v minimum equals square root of rg. So that's our V minimum. So the minimum energy that we need at A, H min, should be equal to the total energy at B, which is the gravitational potential energy at B, 2R times mg, plus the kinetic energy at B, which is 1/2 mv squared. So substituting GR for V min squared, we simplify this too, as I said, pi over 2, it's 2.5 mgr. So that's your minimum height that you need. H minimum is 5.5. So it's 5 over 2, it's 2.5 r. If there's anything more, you'll have a greater speed when you reach B. Next calculation, H is 3.5, R is 14. Calculate EA, mgh, that's the initial potential energy. Go all that and not B, we are at C. At C, we have a kinetic energy and we have a potential energy, but the potential energy is mgr, not mg2r, because you're halfway down. So it's 1/2 mvc squared, whatever Vc is, plus mgr, equate the two, solve for Vc. Turns out to be some number. Yeah.
If we assume that there's like safety guards so that the car can't fly off, would 2R be sufficient? If would be H equals 2R be sufficient to keep it moving once it got to the top?
It'll be about the limiter. So you need a little more to have at least some speed to keep it going.
Okay.
Because you were saying that there is another force in the problem that takes care of that normal force.
Yeah, so if it's got like a second set of wheels to keep it on the track,
and
and
then it there, it doesn't fall off.
so if it was 2R, it would get to the top and then it just stop.
Correct.
Okay.
You need slightly more. So in that case, yes, that'll be the limit. 2R would be the limit. You would say in practice, yes, you need slightly more. But that would be the limit. But then what you're saying is, yeah, it's a more complicated problem. There is another force in the problem that takes care of this, staying on the track. Correct. Okay, so that's that. That's one. So that finishes, and that's probably, let me take 5 minutes and introduce, because we already have these pre-lecture videos on Unit 6, which you would have gone through or you should go through. What I would like to do is to spend just about, like, say, 5 minutes or a little more just reviewing that material. There isn't a whole lot because we learned that by doing stuff. We're going to be doing problems. So what we will do is to spend a few minutes just reviewing the basic concepts and take a break and come back. And we will again return to exactly the same concepts, but this time in the context of problems. Okay, so that's the plan. Okay, so let me see, do I need to write anything? If I do, I'll throw it by. Okay, so what are the ideas in this next unit? Unit 6. It has to do with impulse and momentum. As I said in that introductory video, this is a third way of describing motion. We started off initially with what we had in exam 1. We started off with Newton's laws and acceleration and velocity. That was a full program. If you know all the forces acting on an object, you can use Newton's second law to calculate its acceleration. And in principle, you can integrate it twice with respect to time to get its velocity and position, and you know everything about the motion you're done. But in practice, it doesn't always work. It's not easy to do. The other way we looked at it is using this concept of work and energy. It's easier to do, but you don't get the full amount of information that you did with the velocity acceleration, with the dynamic approach. But when it works, it's great. You can get your answers with much less work, and you're dealing with scalars. And there, all we said was that, okay, if a force is acting, our forces are acting on an object, they do work. That work depends on the force, it depends on the displacement. And if you can calculate the work done, from that you can calculate the change in the kinetic energy. Or the other way around, if you know the change in the kinetic energy, you know the work done. And that's what you use to study the motion in terms of work done and the change in the kinetic energy. But you see, that is something that happens in space. The force acts over a certain distance. The effect of the force over a certain spatial interval. But now what you're going to say is that supposing you have this force that acts for a certain time. We are interested in the time duration of the force. And as I said in the pre-lecture video, it's particularly important when we are dealing with short duration interactions, like collisions, something that happens for a brief time. In such cases, it turns out that we can characterize the effect of the force, the cumulative effect of the force acting over a certain time, as something called impulse. And it's simply the integral of the force over time, over that time interval. The integral from t initial to t final of force over time. That's what we call the impulse. Okay. What does the impulse do? We said that work changes kinetic energy. What does impulse change? What property of the object does it affect? Well, it turns out it affects this quantity called momentum. The most direct way to look at the effect of an impulse is in terms of this quantity called momentum, which for our purposes is simply mass multiplied by velocity. It's a very simple formula. So just like kinetic energy was 1/2 mv squared, momentum is mv. The big difference is kinetic energy was a scalar, momentum is a vector. It's mass times a vector velocity. So remember, momentum and the corresponding quantity impulse are both vectors. So in general, when you do calculations, as we will see when we work out problems when we come back, you have to keep track of directions. So when you apply the impulse momentum theorem, you have to consider what happens in the x direction, what happens in the y direction, and in principle, what happens in the z direction. So you have to keep track of directions and components when you do those calculations because they're vectors. But the point is that, yeah, so there is this impulse mv, there is this momentum mv, and if you apply an impulse to an object, it changes its momentum. And that's the impulse momentum theorem. Change in the momentum is the impulse. But why is it useful? I told you it's particularly useful for short duration interactions where the forces involved are relatively large. So we have large and complicated forces that we can't simply write down as mg or kx in some simple formula. They're more complicated forces, variable forces. So we don't know the details of the force, but we still would like to say something about what the force does, get some information about the force, and that's what the momentum impulse theorem helps us do. Because what the momentum impulse theorem says is that if I know the momentum before the collision or before the interaction, and if I can calculate the total momentum after the interaction, which is relatively easy to do, that difference is the impulse, and the impulse is integral f dt. So I know something about the force, the cumulative effect of the force. But more than that, I can say, well, supposing I replace whatever variable force by some hypothetical average force. What I'm really interested in is what's the average force acting during this collision. So then it becomes a constant. That F average is a constant. I can pull it out of the integral. And I can then say that F average multiplied by the duration of the collision equals the impulse. And we just said the impulse is just the difference in the momentum. So once I calculate the momentum before and momentum after, I can determine the impulse. Impulse is average force multiplied by the duration of the collision. And if I can estimate the duration of the collision, again, which is not difficult to do, like a millisecond, half a millisecond, whatever, once we estimate the duration delta t of the collision, I can take the change in the momentum, divide by the delta t, and I have an estimate of the average force involved. So, though I don't know the details of the force, I have some understanding of what that force is in this collision. And that's how we will use the momentum impulse theorem. Okay, but that's our first part of the topic. That's momentum, and it's connected to impulse by this theorem. But as I said, it turns out that the momentum is actually a very important theoretical quantity. When we do theoretical mechanics, when you do more advanced treatments of mechanics, of Newtonian mechanics, and not just Newtonian mechanics, when you study, say, relativity or quantum mechanics, turns out this idea persists. This idea of momentum turns out to be very deep. It's not MV anymore. It's a more complicated quantity, something else altogether. But its essential nature is still the same. It's a measure of the motion, and it turns out to be a fundamental quantity that you use to describe that is used in physics. And in fact, in advanced treatments of physics, we talk much more about momentum than we do about velocity or kinetic energy. So it turns out to be a fundamentally important quantity. But what's the most important thing about momentum is that if you have an isolated system, if you have a system where there are no external forces or the external forces are negligible, if all that matters are whatever is going on inside that system, turns out all those interactions inside the system will not change the total momentum of the system. So there is this theorem, there is this principle called the conservation of momentum. Just like you have conservation of energy, there is a fundamental principle of nature called conservation of momentum, which says that if you have a system that is isolated, that is where the total external force on it is zero, the net external force on it is zero, or in practice where the net external force is negligible, you can say that you can claim, you can show that the total momentum of the system, not the individual parts, not P1 of part 1 or P2 of part 2, but the sum of all the vector sum of all the momentum turns out to be constant in time. Okay? And that turns out to be an important principle. And what we will do for the rest of the unit is just apply the principle. We're going to be looking at collisions, taking that as an example of the kind of phenomena we study using these techniques. We're going to look at various collisions. And we're going to apply conservation of momentum to study these collisions. Okay. When I say collisions, again, I've dealt with this in those videos. All I mean when I say collision is something that takes place, an interaction that takes place for a short duration of time. And during that time, when the interaction takes place, you can ignore all external forces. You can ignore gravity or whatever external force is present. The only thing that matters, the only forces that matter are the collision forces. But all of that description works perfectly well for the opposite of a collision, which is an explosion. When something blows apart, at that event of the blowing apart, it's a short duration event, and the explosive forces are dominant. So whatever we talk about, well, all these ideas we said about conservation of momentum and this whole procedure works perfectly well for explosions, and we will look at those too.
Are we ever going to get a problem where there's a collision and then something terrible happens and there's an explosion immediately after?
Yeah, we will. If something like that, we'll probably take it as two separate things. The collision will be one interaction followed by another interaction. I don't think we do problems like that, but you can imagine something like that, sure.
Okay, but
Something colliding and blowing apart, sure.
for the purposes of test, would you put those two things in one?
No, I don't remember having done that. It's always because when we have these problems, it's typically one interaction. So it's either a collision or it's an explosion. Typically. Okay, so let's stop there, let's take a break, and we'll come back and continue. Okay, so as I said, I'm going to go on to do problems, but again, given the fact that we have spent more time than I expected on the earlier unit, I might do things in a funny order because some of these demos here are such that, they have to do with collisions, which actually comes later. We'll be doing problems and collisions later. But to understand what goes on there, you don't really need to, it's more of a visual understanding of what a collision is and what are elastic collisions, inelastic collisions. So we can actually talk about those before we start doing numerical calculations, which is what we'll do so that we don't need to come back and put all this up again. So let's talk about that. When we left, we were talking about collisions. So let's continue talking about collisions. And then before we start doing actual problems, we will come back and do that demo. And that is a conceptually important part. We'll come back and I'll ask you a poll everywhere question, and then we will do a little demo. And there is something important. There is a subtle point that you need to be aware of, which we'll talk about. But first, let's continue with collisions. So we said that collisions are brief interactions in which total momentum is conserved. So we'll always use that fact. So if you hear the word collision or explosion, assume that you're going to be using conservation of total momentum. You're definitely going to be using that in any of these problems involving collisions or explosions. And from now on, I'll just say collision. If I say whatever I say about collision also covers explosions. Okay, but in collisions, if you have gone through the video or the notes, you will see there are two classes of collisions. The common ones, the realistic ones, are what are called inelastic collisions. What does that mean? When you say inelastic, what we really mean is that when two things collide, typically there is some deformation or is some energy lost to heat or sound or other forms of energy. So when the objects come in with a certain amount of kinetic energy, they don't retain, the system doesn't retain all of that kinetic energy. Some energy is lost to some other form. In explosions, it's the other way around. Some chemical energy or whatever is converted to kinetic energy to blow the things apart. So anyway, the point is that kinetic energy before the collision is not total. Whenever I say kinetic energy, I mean the total kinetic energy before the collision is not equal to the total kinetic energy after. That's your typical case. And that's what we would call an inelastic collision. For instance, here, if I turn it around, this is an inelastic collision because these two Velcros, when they start, there was some deformation in that. And now, in fact, they actually stuck together. So if I do this, and I'm not doing numerical calculations, but if I did, you will see that if the total kinetic energy before will not be equal to the total kinetic energy after, because when they came together, there was some interaction, some sticking between the Velcro pieces, and some energy was lost. Whereas sometimes we can actually set up, here. We have one of these cameras set up to that. Yeah, there it is. These hard balls, these cool balls here, they're such rigid objects. It turns out, for the most part, they actually retain kinetic energy. Not 100%, it's not perfect, but much better than what you saw there. So when these collide, turns out that the total kinetic energy of the system is actually conserved to a good degree. And such collisions are called elastic collisions. So they're a special class of collisions. And the thing to remember is when you have an elastic collision, you actually have two conditions. One condition is, as always, conservation of total momentum. You can always use that for collisions. But for elastic collisions, you have another condition. And that says total kinetic energy before equals total kinetic energy after. There might be, during the interaction, weird things might be going on. Things might get deformed and recover. We're not saying anything about them. We don't care. That's the whole point about studying collisions this way. We only care about before and after. We don't really care about what goes on during the actual collision. But what we're saying is that whatever kinetic energy we started off with before the collision is what we will end up with after the collision. And that class of collisions are called elastic collisions. And we're going to be looking at both kinds. Turns out that elastic collisions are more complicated. They're harder to work with than inelastic collisions. Inelastic collisions are very simple. You'll see that we'll do a bunch of problems. Elastic collisions involve more complicated calculations. So we're not going to really get into the gory details of it. What we are in fact going to do is to look at a particular case where, switch back.
What is that type of collision called
Which one?
with the two cars?
Initially, what I showed you was an inelastic collision because those Velcro pieces, there was some sticking between them. Some energy was lost. But if I turn it around, this has been, you can see there's been taped over. So that is to create something close to an elastic collision. So the collision between these two objects, now it's actually elastic. Well, there's more going on here. There are magnets, and that's how they're kept apart. So we won't go into the details of it, but we have engineered to have something that's pretty much of an elastic collision. And the interesting thing about this, and this is a calculation we can actually do maybe next time, when we get the formulas, we'll see that. So now they are of roughly equal masses. And what we're going to do is to keep one of them fixed. And this is, remember, we have set it up so that it's close enough to an elastic collision. We're going to just make this cart move. So we're going to have one cart moving, one cart stationary before the collision, and see what happens. You see that the exchange rolls. The one that was moving stops, and the other one takes off. Yep. So once again, you can see it almost comes to a dead stop, and the other way. And that's something we will actually prove when we write down the formulas next time. We'll actually show that when you have equal mass objects undergoing an elastic collision, if one is at rest and the other was moving, they switch roles when they collide. The one that was at rest starts moving, the one that was moving stops. And we'll prove that by using those two conditions. We will use the conservation of energy, conservation of kinetic energy, and the conservation of momentum. But as I said, actually doing the calculations is mathematically more messy than what we are normally used to. So what we are going to do, because we are really more interested in the principle and the conceptual understanding rather than the algebraic details. So what we're going to do for our purposes is we're going to just look at a very specific, very special case of elastic collisions. And that is the one we just looked at, where one object is at rest and the other is moving. Not equal mass. We will generalize that too. They can be arbitrary masses. But we're going to look at cases where, well, here is an arbitrary mass one. So what you saw here was a massive object collided with a lighter object, and after the collision, they both continued moving. Whereas if it's the other way around, if it's a light mass colliding off a heavy mass, you will see something else happen. It bounces back. All these things we can actually do numerically with those formulas. We can get these results. We can see what happens when equal mass objects collide, when a light object bounces off a heavy object, when a heavy object barges into a light object. But in all of these things, just to keep things simple, we're only going to look at cases where one object is initially at rest and the other one's moving. And for that, what we're going to do is just write down the formulas. The formulas are derived in your book. You will see there is a bit of algebra there. We're not going to reproduce the algebra here. I'm going to just code those formulas, and those formulas are available in your equation sheet. So as far as elastic collisions are concerned, you're going to look only at this special case of a moving object colliding with a stationary object. As far as inelastic collisions are concerned, anything goes. That's an easy thing, easy calculation. So you'll look at moving objects, both objects moving, one object moving, you'll look at everything. But for elastic, it's going to be this case. A moving object colliding with a stationary object, and then they both start. Okay, that's the idea. So let's come back to this, and before we go on to problems, let me just talk about one interesting, again, I'm not going to prove it today. If I get time, I'll discuss it next time. But it's an interesting feature that we look at, which we can actually prove using conservation of momentum and conservation of kinetic energy. And that is, if you take these balls, if I take one ball here, and if I let it go, you would expect that if I hit it hard, the harder I hit, the more balls I should be able to move. And if I just do it like this, I'm able to push one ball off. You'd expect that if I really hit it hard, maybe I can make two balls move. But that's not what happens. However hard I hit it, one ball coming in results in one ball going out. And let's do another one. Start with two balls. Two coming in results in two going out. And so forth. Three. So that symmetry, balls coming in equals balls going out, is actually a consequence of applying the conservation of momentum and the conservation of kinetic energy to these processes. It's a little more than that. I'm not giving you the whole picture, but for a good approximation, that's all you need to prove this. Yeah.
What happens if you take an equal amount on both sides and let them go so that they come together at the same time?
Keep it, and if they are, maybe they'll stop. I'm not sure, actually. It's a good idea. But I'd keep it symmetric. I'm not sure I'll do that. Yeah, that's exactly what I was hoping would happen. Because once that gets tangled, it's a real pain to untangle them. So let me not mess around with it too much. But but in principle, what you would be, it'd be hard to arrange. But if you were to arrange equal masses going in opposite direction, just come to a stop because the total momentum is zero to begin with. And once they hit each other, they should either what that proved, no, it's not true. What happened there was perfectly fine. They can bounce back with equal speeds. But the total momentum should always remain zero. There should be a symmetry. Okay, so what do we do now? So let's go on to start talking about back to impulse. We start doing problems on impulse and momentum, the impulse momentum theorem, and then gradually we'll work our way into collisions and conservation. Because conservation of momentum is not really an independent topic. It's a principle that we apply to understand collisions. So it's really after we get through the impulse momentum part, it's all collisions. Right.
Regarding the inelastic collisions, are they inelastic because friction and air resistance and whatnot steal forward momentum so that there's less to pass on and keep the system?
The point is that the momentum part, before they collide and after they collide, all those forces are important. But during the collision, all those forces can be ignored. We are saying that the collision forces are so large that we really ignore friction, gravity, whatever, during the collision. I hear tension, for instance. When they collide, there is tension in the strings. We completely ignore those.
Okay, just relatively.
But before and after, yeah, they're important. And we're going to be actually doing problems next time where we'll actually look at a system. We will do a demo. We'll look at a system called the ballistic pendulum, where during the collision, we'll use conservation of momentum. But after the collision, we'll use conservation of energy. So we'll treat it differently before and after the collision.
Okay.
So the gravitational force will turn out to be important after the collision. but during the collision, they'll neglect it.
Okay.
Okay, so pull everywhere question. Back to, this is +5 to unit 6. First, it's a long question, but it's related to that demonstration. Turn the lights and put it.
Jesus. Oh my.
So as I said, it's phrased in a long-winded way, but essentially, you're throwing something at a door to try to open it, and you have two choices. You have either something that sticks to the door or something that bounces back. The question is, will they be equally effective, or will one be better at opening the door? A sticky ball of clay and a super bouncy ball. And which is preferable to open the door? That's the idea.
This
Yeah,
gives me
it's great.
anxiety because I have a pet.
So as I said, what we're going to do is, no one, think about it, but we're going to do a demo which will actually answer the question. So the whole point is that the same mass, everything is the same, you're throwing with the same speed. The only difference is that one ball hits the door, sticks to it. The other one bounces back. Does that matter? And what you want to do is the one that makes the door open faster, the one that's better at opening the door is what's important.
Yes, I always sleep with my one bouncy ball next to me.
That's right.
So is the fire included in the demo or?
Luckily not. It's a much tamer demo. So we're going to try to knock this board over with two kinds of balls. That's all we're going to do.
No
So
fire.
there are these, so one of these balls, you can see there are copies of these. One of these bounces, one of these sticks, just stays, doesn't bounce. So we're going to compare. So this one is a bouncy ball, that's a sticky ball. We're going to see what difference it makes. But let's start with the,
Are they pretty big? These example balls? Are they? Because if it's like, because my life depends on those little things, then I.
oh, no. I guess they're big enough to.
It's like, because I guess I'll make my peace.
And the fun part, I hope the demo has been set up right and you get what I want. Let's just hope it works the way I want it. Anyhow, and I'll explain it anyway. Okay, so let's get to the demo soon.
Some physics questions, I'm just like, these are terrifying. Like the elevator you're in snaps.
That's right. Always fun.
I don't want to think of
Engineering and OSHA questions.
Yeah, you're riding a roller coaster.
They'll fall off.
Or like the one where you're just like throwing cannons at stuff, and I'm like, why are you walking around with like ye olden times ballistic stuff? Ye olden times. What are you doing?
Okay. Oh, did I have to open? No, there it is. I didn't count the responses. Okay, let's see what it says.
Oh, dang.
It says the Super Bowl. Let's see what it is. So let's have a demo. And hopefully it'll work the way it's expected to. The hope is that that bouncy ball, which is kept here, this is the bouncy one, just to make sure that we know what it is. There's a smiley face on it. And so the hope is that, that's what Sean did. And the hope is that that will knock the board over, but the sticky one won't. But as I said, it all depends on the setup. You might end up, both of them might end up knocking it over, both may not. But let's hope it works the way we expect it to. In any case, I'll explain why we expect it to work that way. Now we make sure, this other board is to make sure that we both start them off with the same potential energy so that they have the same kinetic energy when they reach there. And that helped. Then knock it over. And let's just hope the other one works as intended. Same initial condition. And it worked. Good. So that shows that, you have to believe me about that. The way the masses are the same, and I did start it off at the same position. So the initial energy, potential energy was the same. So the speed was the same when it hit the board, and it hit pretty much at the same point. And we found that this was able to knock the board over, the sticky ball wasn't. But what that means is that this bouncy ball transferred a greater momentum. That's what we conclude. So whether it fell over or not, or whether that door in the example opened or not in the question, depends on the amount of momentum that was transferred to the door. What it says is that the bouncy ball is able to transfer more momentum to this board than the sticky ball. So why is that? That's an application of the impulse momentum theorem. So let's go ahead and work that. In fact, there is a calculation we'll do that. The first homework problem, not homework, the first work problem has to do with that. But first, let's do that algebraically without numbers. And this is a point that you need to be aware of, should be careful about when you do problems with impulse and momentum. They're very simple problems. The calculations involved are very simple, but this is the one thing that you need to be careful about. Okay, so let's see. So you have something, board, wall, something, a door. Ball going towards the wall with the initial speed vi, and it hits and bounces back. Speed vf. And about mass m. So it goes in the positive direction, hits the wall, bounces back. And what we're interested in is the amount of impulse that the ball exerts on the wall or corresponding the wall with the ball. They're equal and opposite. So remember, what does that depend on? For the impulse momentum theorem, vector J equals to P final minus P initial. Put those arrows over there to remind myself that these are all vectors. They're all one-dimensional, but they're vectors. So when I write these down, I have to be careful. I have to say that, well, PF, in my notation, that's going that way is positive. So VF is a negative. It's a negative moment. So when I write it out with positive and negative signs like we usually do in one dimension, remember in more than one dimension, we put arrows on it because it's some direction. But in one dimension, how do we indicate direction? By plus and minus sign. Is it in the positive direction or the negative direction? Now, VF happens to be in the negative direction. So we would say this PF will be negative MVF. But VF is this is the speed. So the symbols VF and VI, those are numbers, those are positive quantities. They refer to the magnitude. So that's why I need a negative sign in front to tell myself, to remind myself, to take account of the fact that the final momentum is actually in the negative direction. And now I say minus the initial momentum, which is in the positive direction. So in fact, that's what it is. So when something bounces back, the change in the momentum is in terms of magnitude, is the sum of the two. It's negative minus a positive, or the other way around. You could have taken positive in the other direction, in which case you would say, which is positive minus a negative quantity. So either way you'll add. The point to note is that before and after the collision, the momentum points in opposite directions. So in terms of numbers, you're actually adding the numbers, not subtracting one from the other. So that's why. So now coming back to this demo, in one case, VF was 0. It never bounced back, just stayed where it was. So VF was 0. So the transfer of momentum was just MVI, negative MVI, but we are interested in magnitude, MVI. Whereas when it bounced back, no matter what it bounced back with, it bounced, the effective transfer of momentum was greater. It was MVF plus VI. So when something bounces back, the change in the momentum is in magnitude, the original momentum plus the momentum that is imparted in the other direction. So that's why a bouncy ball transfers a greater momentum than a ball that sticks. So the point of this is when you do calculations, remember, when you do calculations with impulse and momentum, the direction matters. So when you subtract final momentum from initial momentum, keep track of the signs. If they're in opposite signs, effectively you're going to add them. That's it. And we can go on and do problems.
Sorry.
Yeah.
So I got the right answer, but my reasoning was because the sticky ball would deform, and that deformation would kind of steal any energy that could be transferred.
Yet again, but the point, remember, in this discussion, at least in the approximation we are using, we're only talking of momentum. What's happening to momentum? What if momentum does it impart?
Okay.
So that part is still.
Okay.
But kinetic energy wise, we should be able, but the point is that, yeah, if you think about it, you should be able to formulate everything, because all of these are alternative ways of doing the same analysis. So you should be able to formulate it in terms of kinetic energy also. Perfectly fine. So what you're thinking is not wrong.
No, that's
Okay, so problems. Again, just to save time, because I've written those problems out in great detail, rather than repeat stuff on the board, I'll just go ahead and step through the slide. Because the initial problems are really quite simple. Okay. So this is, instead of horizontal motion, it's vertical. So take a steel ball of mass 40 grams and is dropped from a height of 2 meters onto a horizontal steel slab. The ball rebounds to a height of 1.6. So obviously some energy has been lost. Because it starts at 2, bounces back to 1. So there is a loss of energy in the collision. So what are we looking at? We're going to calculate the velocity of the ball just before it hits the ground, velocity of the ball just after it leaves the ground. Using that, we are going to calculate the impulse delivered, which is the change in the momentum of the ball. And finally, we're going to use this information, use the impulse information to estimate the average force. That last part is the easiest one. It's typically just taking the impulse and dividing by whatever time they give you. In this case, it's 2 milliseconds. Okay, what about the first part? Now, at this stage, you have studied free fall. You know about the equations of free fall, the equations of constant acceleration, but you also know about kinetic and potential energy. So for A and B, it's really up to you what you want to use, whatever you're comfortable with. Typically, energy methods are easier to use because all you have to say here is mgh, which h equals 2. That's my initial energy, initial potential energy. Mass times g times 2 meters. That is equal to 1/2 mv squared before it hits the ground. So 1/2 mvi squared equals mg hi. That's it. Calculate that, find out what my b is. But if you like, you can do the way you would have done it earlier, knowing the height, you can calculate the speed. It's just really equivalent if you think about it. But so the point is, when you're doing calculations with momentum and stuff, when it comes to freely falling bodies or constant acceleration, you have a choice of either using dynamic methods, constant acceleration formulas, or energy methods. So anyway, so we use that and calculate the speed before it hits the ground. What about the reverse part? Again, it's just the opposite of what happened. You're starting off with the kinetic energy at the ground. As it goes up, it gets converted to potential energy. Finally, you have zero kinetic energy. And all of it is converted to mgh, where h is 1.6. So same formula, 1/2 mv squared equals mgh with h equals 1.6, and you determine v. So you have v initial before the collision, v final after the collision. But what you need to remember is that these are in opposite directions, just like we did for this collision. vi is downward, vf is upward. So when you take the difference, it's going to be vf minus the magnitude of vi. So not vf plus the magnitude. It's going to be vf minus vi, m is common to both, but that is going to translate to vf plus the magnitude of vi because vi is in the negative direction. So you're going to be adding those numbers when you do part C. So let's look at that. Conservation of energy, 1/2 mv squared equals mgh, v equals plus minus square root of 2gh. That applies to both upward and downward motions. Downward, we'll take the negative root because we know it's going down. So that's v before the collision is negative 6.26, h is 2. For the upward motion, h is 1.6. You get 5.6, which is positive because it's going upward. Now we calculate the change in the momentum. We calculate the impulse, and that's when we remember that it's negative of negative 6.26. So we're going to be adding those numbers. That gives us the impulse, which is in kilogram meters per second, number 6. Mass. So momentum doesn't have any units of it. It's an important quantity, but there are no special units of it. You don't have newtons or like we had for other things. It's just mass. It's kilogram mass per second. Mass in kilograms, speed or velocity in meters per second, it's kilogram meters per second. Web average, I told you, just take the time they've given you, divide the impulse by the time, and you get the force. So this is just an estimate of the collision force, what happened when the ball collided with the steel slab. That's a one-dimensional calculation. But we said these are, by nature, vectors. So what about more than one dimension? What about impulse and momentum calculation in 2D? So you have a case where a bat strikes a ball. We take the ball to be moving horizontally, it hits the bat and takes off at an angle, 30 degrees above the horizontal. Hopefully there's a picture here. Yeah, there it is. Ball's coming in with the velocity vi in the horizontal direction. Vf is at an angle. Then they're going to ask you to calculate the impulse. This is a two-dimensional problem. So what that means is that Vf will have to be split into two components. Vf will have to be resolved into a horizontal component, a vertical component, Vfx and Vfy. And you'll be calculating the impulse Jx in the x direction, which will be Vfx minus Vix. Vix is just Vi. There is no Viy. It's in the horizontal direction. So Vfx minus Vix will be one calculation that'll give you the impulse in the x direction, Jx. The other one, Vfy minus 0, because there is no Viy. That'll give you the impulse Jy. So you're going to get an impulse in the x direction, which will be which will be the change of momentum in the x direction, the change in the x component of the momentum. And you're going to get impulse in the y direction, Jy, which is the change in the y component of the momentum. So you'll have a jx and a jy. What's left? If they ask you for the, I think they've asked you here, they'll ask you for the magnitude of the impulse. Any vector, once they give you components, they can ask you for the magnitude and the angle. Usual thing. You use the Pythagorean formula and the arctan formula. Arctan of jy over jx will give you the angle made with the horizontal. That's it. So conceptually, it's nothing to it, but obviously the calculation is a little more complex than what we did in the last problem. So there you are. Vix is 40, Viy is 0, Vfx is negative 52 cosine 30, because 30 is the angle made with the horizontal. And from the direction of Vf, we know that the x component is negative, y component is positive. So Vfy is 26, and Vfx is negative 45. They've given you the time as usual. They said the time of collision is 1.75 milliseconds. Jx is mfx minus m times vfx minus vix. Remember, again, when you do that calculation, they are in opposite directions. Vix points to the positive direction, Vfx is in the negative direction. So when you take that difference, when you subtract, you're actually adding the numbers. So you're taking a negative number of Vfx and subtracting a positive number from it. Vy is easier because Viy is 0. So it's only Vfy, it's m times Vfy. So you get your Jx and Jy. You calculate the average force. I mean, this part could be done in two ways. You could do your Pythagorean theorem and calculate the net. You can calculate the magnitude of the impulse and then divide by the time to get the magnitude of the force. Or you could calculate like they've done here. You can calculate the x and y components of the average force and then apply the Pythagorean theorem. The order in which you do it doesn't matter. So here they calculate the average force in the x and y direction, the components of the average force. And then they use the Pythagorean theorem to calculate the magnitude of the average force and the arctan formula to calculate the angle, the average force. And what you find is that the average force obviously is not in the direction because it partly pushes it back and partly pushes it up. So the force is somewhere in between. So it's not 30 degrees above the negative x-axis. The force is 17 degrees because it has both a vertical and a horizontal component. Do we have time for this? Let's take a look at this. Is very simple. Let's take a look at this and then we'll continue next time. So this is we formulated as a conservation of momentum problem, but it's really like an explosion. Something separates out. A bullet exits from a rifle. That's a brief interaction. So this is an example of an explosion. So you have a rifle of mass 3 kilograms, fires a bullet of 5 grams. Initially, they are at rest. The total momentum is 0. They go apart. The speed of the bullet is 300 meters per second. The point is that you know there has to be a recoil. The rifle has to go back because initially you started with 0 momentum, total momentum. And if one object moves to the right with whatever speed, there is a non-zero momentum to the right, which has to be compensated by an equal momentum to the left. Okay. So the rifle will recoil back with a much smaller speed, but it will go back. It has to compensate for that momentum. So that's what they've asked you to calculate, the recoil speed. And then they've asked you this interesting question. You have this massive rifle, which is 3 kilograms, and a bullet, which is much lighter than that, 5 grams. So the bullet's traveling a lot faster, but the mass is a lot smaller. The question is, which has a greater kinetic energy? Does the rifle have a greater kinetic energy, or does the bullet have a greater kinetic energy? Okay. But this actually, I mean, it's worth, before I do this, it's worth talking about. You actually asked this question earlier, so when we talked about the apple falling toward the earth, we had the same discussion. We said that, well, the apple is tiny compared to the earth, and falls toward the earth, so we can sort of guess that the earth is not really going to be moving much. But then what are the numbers? Right. Yes, the apple's moving a lot faster than the earth. That sort of makes sense. The earth hardly moves. What about the kinetic energy? Same question. The apple's moving faster, the earth is moving slower, but the mass of the earth is enormous. So which has more kinetic energy? So you have to compare the velocities of the two objects, the kinetic energies of the two objects, and the momenta of the two objects. So how do you compare those? The thing to remember is that in a closed system, total momentum is conserved. The critical principle to use is conservation of total momentum. So if you consider the Earth Apple system to be a closed, isolated system, forget about the sun and all of the influence. The sun really doesn't matter because the Earth and the apple are both falling toward the sun, but moon or whatever other objects, Jupiter. But if you consider the Earth and apple to be a closed system, to begin with, if they are at rest relative to each other, the total momentum is zero. And as the apple and Earth fall towards each other, the total momentum is still zero. It's really exactly the same case as this bullet gun exam, this problem. They're going in opposite directions, but it's exactly the same. The total momentum is still zero. So in terms of magnitude, the momentum of the apple is equal to the momentum of the earth. It's equal and opposite. They are in opposite directions, but they are of equal magnitude because they have to add up to zero. So what we say here is that if you have an apple, earth, in conditions like these, or this rifle bullet case, the condition you will use in cases like this is that the magnitude of the momentum of the apple equals the magnitude of the momentum of the earth. That's the condition you use. So the magnitude of the momentum of the rifle is equal to the momentum of the bullet. Well, what does this mean about speeds and kinetic energy? Speeds is, say that that's mass of apple, speed of apple, equals mass of earth, speed. So that tells you the ratios of the two. So this speed of the earth compared to the speed of the apple is equal to the mass of the apple compared to the mass of the earth, which is much, much smaller. The apple is tiny compared to the earth, and that's how we show that, yes, in fact, as we expected, the speed of the earth is negligible compared to the speed of the apple because the ratio is given to the ratios of the masses. So that's the condition that finally helps us prove that statement. Okay, what about kinetic energy? This is where, if you look at the notes, I've actually proved this. It's there in the notes, the video. It's a very useful formula to remember. And that is K, which is just 1/2 mv squared. By multiplying and dividing by m, you can actually write this as 1/2 m squared v squared divided by m. Multiplying top and bottom by multiplying and dividing by m. But then m squared v squared is mv squared, m times v squared. That is momentum squared. So this is actually equal to p squared over 2m. So that's a nice relationship to remember. K equals p squared over 2m. How does that help? That helps us answer this question. We can say that K earth divided by K apple equals, remember we already said P is the same for both, equal to some common P. That's our starting condition. So we say this is equal to P squared over 2m earth divided by the same P squared over 2mf. If you simplify this, like one fraction over another, something like that. That turns out to be equal to 1. That's what's interesting. It turns out that the kinetic energy of the Earth, the ratio of it to the kinetic energy of the apple, is inverse of the masses. So just like velocity, the kinetic energy of the Earth is negligible. So the speed, essentially the only thing that's moving is effectively just the apple. And the kinetic energy is effectively entirely in the apple. You can forget about the kinetic energy of the Earth. Same thing, let me take 2 minutes to finish this problem, because exactly it's what we're going to use in this problem. Instead of the Earth and the apple, we're going to use a rifle and a bullet. So recoil speed of the bullet. Condition we use, total momentum is 0 before the bullet's fired. It'll continue to be 0 after the bullet is fired. So M rifle, V rifle plus MV, M bullet, V bullet equals 0. The recoil velocity is given by that formula, MPVB divided by MR. And it's obviously very small. It's half a meter per second. The bullet is moving at 300 meters per second. The rifle is moving at half a meters per second, but it is moving back. Kinetic energy. So we work out the kinetic energy of the rifle, 0.375 joules. The kinetic energy of the bullet is 225 joules. And just like we saw in this Earth example, most of the kinetic energy released is in the lighter object. It's in the bullet, not in the rifle. And that, we'll stop at that and start with this problem.